In the last video, we derived a simple relation that T sigma is equal to A nu and it is greater than 0. It was equation number 23. So, from this equation, it is evident that when both A here, which is affinity, and nu, rate of reaction, are positive, if this is also positive and nu is also positive, it simply means the reaction occurs from left to right. Or you can say from reactants to products. If, however, both these quantities, that means affinity and nu, are negative, the reaction takes place from right to left, you can say, or you can say from product side to reactant side. Now, if we take a condition, if this affinity is equal to 0, the reaction is in a state of equilibrium. If nu is equal to 0, it does not necessarily mean that A is also 0. You have to remember this, that if nu is 0, it simply does not mean A is also 0. If now we take a condition nu is equal to 0 and this affinity is not equal to 0, this is basically a simple case of false equilibrium. Case of false equilibrium, you can say. We also derived in the last lecture an equation which was the dis upon dt is equal to A by t d zeta upon dt, which was also greater than 0. In the last video we named this equation as equation 18. So you can follow from that lecture also. So this equation, basically this equation 18, can be extended to several reactions, but these reactions should occur simultaneously, occurring simultaneously. Suppose if we have R reactions, and if we name them as, suppose row will change from 1 to 2, 3, 4 up to R, and these are occurring simply simultaneously. We can simply transform this equation 18 that dis will be equal to 1 upon T summation of rho A rho d zeta rho greater than 0. This is equation number 25. Here A rho is affinity of the row reaction. Related to chemical potentials. By simple this reaction, that means A rho will be equal to minus summation of gamma mu gamma and rho and chemical potential mu gamma. Okay, this is 26. Now if we take an equilibrium state, we know all affinities are, or you can simply remember all affinities will be equal to 0. So at equilibrium state these affinities will be 0, so we can write A1 will be simply equal to A2 will be simply equal to I dash to A rho, suppose, will be simply equal to 0. 27. So the entropy production per unit time is now simply given by that means you can simply write dis upon dt will be equal to 1 upon t summation rho A rho mu rho greater than 0. This is 28. So we see that the entropy production per unit time is the basically sum of the entropies or you can say here entropy productions due to the various reactions. It must be emphasized that the entropy production resulting from all the simultaneous reactions is positive. You have to simply remember, if there are many reactions taking place simultaneously, then the individual entropies are always positive, or you can say the total entropy production resulting from the sum of all these individual reactions is always positive. Now it may happen that a system undergoes two simultaneous reactions. Such that, suppose if a system undergoes two simultaneous reactions, we can write A1 for reaction 1 and its rate mu1. Suppose it is less than 0, that means it is less than 0. Or in the second reaction we can write A2 mu2 is greater than 0. Suppose this is equation number 29. Provided that the reaction sum, that means you can simply sum the two reactions A1 mu1 plus A2 mu2, it will be always greater than 0. This is very important result, that if in one reaction A1 V1 will decrease, but in the other reaction A2 mu2 will be greater than 0, but their overall sum will always be greater than 0 or positive, we can say. These reactions, that means this one A1 mu1 plus A2 mu2 greater than 0, which was equation 30. For these both the reactions, are then said to be coupled reactions. This is very important. So from this all discussion, which was basically from a scientist Redonder, suppose definition of, we used the chemical affinity. We can say this chemical affinity is basically closely related to entropy production. Okay.